or how long it takes the ball to drop to the ground. Okay? Height of the ball, right? And gravity. Now, it's going to take longer for that ball to fall if I'm on the moon. Why? Because gravity is different on the moon. Gravity is a constant. And when we look at variation, we have to find those constants. Another constant is pi, right? 3.14. That is a constant that goes with circles. So we have different constants that we have to find. And so the first type that we're going to look at again is direct variation. And direct variation means one variable directly affects another. We also have joint variation, which is multiple variables going together, and inverse, which are division. So we're going to be looking at direct variation. And this is 3.7. And your formula for direct variation is y equals kx. And k is our constant. So k might be something like gravity. Now this is our basic formula. When I teach variation, I don't use the x and the y. I actually write it out in words what they are. So I'm not just going to put x as a speed. I'm going to write down speed. Okay? Or distance that you travel. Instead of writing a y, I'm going to use the distance. So that way we can keep track of things. The hardest part of this section is keeping track of what goes where. That is, again, the most difficult part. All of these are applications. So we're going to do a couple of direct variation, and then we'll look at direct variation to a power. Then we'll look at inverse variation, and then we'll finish with joint variation. So let's look at question 27, and this is on page 416. All of these are applications. So all of your homework in this section is nothing but applications. And when we work these out, we need to make sure we understand some of the key words. So let's read here question 27 and see why this is direct variation. So question 27. The circumference of a circle varies directly as the radius. A circle with a radius of 7 inches has a circumference of 43.96 inches. Find the circumference of a circle if its radius changes to 11 inches. So what we need to first do is we need to come up with our formula based upon what we have. And then once we find our formula, we'll plug in the new numbers. Now, here's a key word right here. Varies directly. That tells me that this is a direct variation question. If it said inverse, you would have the fraction. It would be an inverse variation question. So the key things we look at first is what type of variation is it. This one's a direct variation. Now, we need to find our k. And what does it say? It says the circumference of a circle varies directly as the radius of a circle. A circle with a radius of 7 inches has a circumference of 43.96 inches. So the circumference varies directly as the radius. So our formula is going to look like this. And this again is on page 416. We're going to look at question 27. Our formula looks like this. Circumference is going to equal, because it's varying directly, to the radius. So that's k times the radius. So this is our formula. Now, what do we know? Okay, when we read this, we're now going to plug our numbers in because we have to find k. That's our first step. Step 1 is find k. That's your constant. So let's see what we've got. Now, what do they tell you about the circumference? It says the circumference is 43.96. So we plug that value in. Now, we don't know the k, so that's going to be our unknown. And what is our radius? Right? Our radius is what? 7. So that's going to go there. Now we can divide and we can find our k. So divide by our 7. And then now let's see what we have for our k. So we're just simply going to take that 43.96 and we're going to divide that by our 7. And that gives you 6.28. And what does our formula look like now? Well, our new formula now is the circumference equals 6.28 times the radius. So that's our formula. And we'll talk here in a moment about that 6.28. And I'm going to show you what it is. What do we want? Well, we want to find the circumference of a circle when the radius changes to 11. So we want to find this circumference when the radius is 11. So that's what we're going to try to find here. So that means we simply plug our value in. So our circumference is going to equal 6.28 times 11. And 6.28 times 11 comes out to be 69.08. And that is your circumference. And that is going to be in terms of inches. Now, what we just found was we found our formula for the circumference. If we go to the back cover of our textbook now, so this is our formula. If we go to the back cover of our textbook, what's our formula for the circumference of a circle? 2 pi r, right? What is 2 pi? Okay, what's 2 pi? 2 times pi is 6.283, goes on forever. That is your k. So that is what we found, okay? We found our k, which is 2 pi in this case, because it's the circumference of a circle with the radius. That's what you found. So we found k. This is how they came up with the value of pi. That's what they did when they first figured out that pi goes into a circle. How do they figure out what it is? Well, they did that by measuring. And they looked at circles and they measured them, and then they were able to actually use, and this is a very elementary procedure, they were able actually to use calculations like this to determine the value of pi. That's how they did it, based upon the circumference. Because in ancient times, they had some simple algebra, and they were actually able to figure it out. Same with gravity, right? They measured how something fell, and they looked at that, and they found out the constant of gravity. This was direct variation. Let's do another one with direct variation, and then we'll look at direct variation to a power. So let me pick another one that deals with direct variation. All of these are a little bit different. Let's look at question. We did 27 here. That was a direct variation question. Let's look at 29. Okay, so let's read question 29. Talk about the resistance of a wire. The resistance in ohms of a platinum wire temperature sensor varies directly as the temperature in kelvins. So if the resistance is 646 ohms at 100 degrees Kelvin, find the resistance at 250 degrees Kelvin. Now, a little bit of background about resistance of current. The higher the temperature, the less resistance there, the more resistance there is. Okay, so they vary together. So one influences the other. So the temperature influences the resistance of that wire. And as one goes up, the other one goes up. So let's come up with our formula. Now we know it varies directly. So when we read these, the first thing we look at is what is it? Is it direct variation? Is it direct variation to power? Is it inverse or is it joint? It will usually tell you in the question with words what it is. So this varies directly. So that means one influences the other one. If the resistance is 646 ohms at a temperature of 190 K, find the resistance at a temperature of 250 degrees Kelvin. So what are we looking at? Resistance varies directly to what? To the temperature. So how do we set up our formula? Resistance varies directly, so that means the resistance of this wire is going to equal K times the ohms. Or sorry, no, K times temperature. Okay, so K times the temperature. And that temperature is in kelvins. Now, what do we know about this resistance? It gives you the starting values. It says resistance is 646 ohms at 190 degrees Kelvin. So that's 190 K. Let's go ahead and find our K now. So divide by your 190. And K may or may not come out to be a whole number. In this case, it comes out to be a nice, easy to use decimal. So K is 3.4. What does our formula now look like? Resistance of that wire is 3.4 times the temperature. There's our formula. Now, what do we want? It says find the resistance at 250 degrees Kelvin. So what are we going to plug in? We're going to plug in that 250. So we have a resistance. And that is unknown. We're going to be finding that. We've got our 3.4, which is our constant. And we're going to multiply that by our temperature in kelvins. And what does that give you out for your resistance? So 3.4 times that 250. Well, that's going to be 850 ohms. And that is your resistance. a lot of times when you work through these, you may come up with some unknown units. We're not used to talking about ohms, but ohms goes with resistance in an electrical circuit. And a lot of times, we don't use Kelvin for our temperature, right? We use Fahrenheit or Celsius. But Kelvin is used a lot in physics and your physical science classes. It goes back to the fact that 0 degrees Kelvin is absolute zero. No movement at all. So it's different than the Celsius temperature and the Fahrenheit temperature. It's a new temperature. But whenever you see that K, that means degrees in Kelvin. Those were direct variation. One influenced the other. As the temperature went up, resistance also went up. Now let's look at 31. And this is going to be variation, direct variation to a power, or a root in this case. So let's look at question 31. The distance a person can see to the horizon on a clear day from a point above the Earth's surface varies directly as the square root of the height at that point. If a person is 144 meters above the surface of the Earth and they can see 18 kilometers away, how far can a person see to the horizon from a point 64 meters above the surface? Okay, so what do we know? Well, if you're on the top of a tall building, you can see a lot further than you can on the ground, right? And it's not just a direct variation, it's a direct variation to the square root. So how much you can see, it varies directly as the square root of the height. So it's not just a direct variation, it's a direct variation of the square root. So what is it going to look like now? Okay, very similar to what we've done before. We need to come up with our formula. What are we looking at? We're looking at how far you can see. So we'll just call that how far we can see. And we'll just say how far you can see. So we'll choose the C there. Is going to equal K times the square root, it varies directly as the square root of the height. So how far you can see varies directly as the square root of the height. I like to use the words instead of the variables x and y, because if you start using x and y, you get really confused as to what went where. So why do that? We can write it out in words. Now, what do we know? We need to find our K. So what do we have? A person is 144 meters above the Earth's surface. So that's your height. And when that person is 144 meters above the Earth's surface, they can see 18 kilometers. So we plug our values in. Now, 144 is a perfect square of 12. So that gives you 12K equals now 18. We'll divide by our 12. And what does that give us for our answer then? And you can either leave it as a fraction, or you can use the decimal equivalent. If it breaks down to a decimal that terminates, it stops, I use the decimal. If it's a fraction that goes, or decimal that goes on forever, I leave it as a fraction. So this is going to reduce down. Okay, so these both have a 6 in common, and so that's going to reduce down now into 3/2 or 1.5. You can either use that 3/2 or you can use that 1.5 in this case because it reduces down directly. Now, what's our formula look like? Our formula looks like how far we can see is going to equal 1.5 times the square root of the height. That's our formula. Now, what do we want? Let's make sure we know what we want. It says we want to find how far a person can see when they are 64 meters above the surface. So I want to find out how far I can see when my height is 64. So we can plug that in. So how far you can see is going to be 1.5 times the square root of 64. 64 is a perfect square of 8, right? Perfect square of 8. So that gives you now 8 times that 1.5. So that comes out to now be 12. So how far can you see? Make sure you're on the correct units of measure here. This is measured in kilometers. So you should be able to see 12 kilometers away. So if you're 64 meters in the air, then you should be able to see approximately 12 kilometers. The hard part is setting up the formulas. That's it. Everything else is really, really easy. Let's look at another one. That was direct variation to a power, because we had a square root there. Let's look at 32. And this one is going to talk about how fast water empties from a pipe. Now, what do we know? We know the larger the pipe, the faster water moves through. Makes sense, right? Bigger pipe, faster it moves through. It actually moves through by the square. So let's come up with our formula. The amount of water emptied by a pipe varies directly, so there's our key word there, directly as the square of the diameter. So it varies directly. I know it's a direct variation. And we're looking at a square of the diameter. For a certain constant flow rate, a pipe emptying into a canal will allow 200 gallons of water to escape in an hour. Find the diameter of the pipe, the diameter of the pipe is 6 inches. How much water would a 12-inch diameter pipe empty into the canal in the same hour? We're going to assume the same flow rate. So what does our formula look like here? Direct variation to a power. In this case, it's direct variation to the square. So I'm going to come up, and again, you can write this up in words. You can use the X, Y. It doesn't matter. I like words. I think it makes it easier. So the amount of water emptied, so we'll just say the amount of water that you empty. So that's going to be our water we empty out. Is going to be K times the diameter squared. So the amount of water that you empty is going to equal to K times the square of the diameter. So what do we know? We know for a certain constant rate of flow, a pipe that will empty in the canal 200 gallons of water in an hour, and the diameter was 6 inches. So the water is going to be 200 gallons. K, which again is our unknown, we have to find that value. And that pipe is 6 inches in diameter, and that's going to be 6 squared. So that is then 36K equals 200. We'll divide by our 36. And now we've got K equals, it's not going to reduce down nicely to a fraction that gives us a terminating decimal, so we'll have to use the fraction. I can reduce this down because we've got a 200 and a 36. Both have a 4 in common. So thank you very much. Okay, so we can reduce this down right? And they both have a 4 in common. So that's going to be now 50 over 9, right, when I reduce with the 4. And I think I can go again. Well, maybe not. Let's see, 50 over 9, that's as far as we can go. I think that's about it. We can't really break that down anymore. That's our value of k. Now, why would I not want to use this? You wouldn't really want to use the decimal because look at the decimal. Okay, the decimal goes on forever, right? If it goes on forever like that, don't use the decimal, use the fraction. If it stops, if it terminates, like this one did, you can use the decimal. But if it goes on forever, just keep the fraction. So what's our formula look like? Your water is going to equal 50 over 9 times, again, the diameter squared. What do we want? We need to always make sure that we answer the question, and we want to increase that diameter to 12. So we want to find the water flow rate when the diameter is 12. So let's plug in our 12 and see what happens. So our water flow rate is going to be 50 over 9, that's our constant, times our 12 squared. And here's the way that I break them down. So we've got 50 over 9, 12 squared is 144, and we'll put that over 1. Just so we don't make a mistake, we'll divide, multiply, and you always divide at the end. So 50 times 144 is your 7,200. 9 times 1 is 9, and that then breaks down into 800. So that means how much water can flow through a pipe in 1 hour? If that pipe is 12 inches, 800 gallons per hour. And units are important, so please make sure you put the correct units on there. So if I increase that pipe by by doubling it, right, we actually increase the flow rate by 4 times. Because at 6 inches, we could get through 200 gallons. If we double the 6, we get 12, but we more than double the output. We got out 800 gallons. That's why it's the direct variation to the square. So that was question 32. Let's talk now about inverse. Okay, and inverse variation looks like this. Inverse variation is y equals k over x. So inverse variation means we've got to divide. So when we work these out, we're going to have to divide. So let's try one of these. Question 34. The current in a simple electrical circuit varies inversely, so very important here, varies inversely as the resistance. If the current is 50 amps, when the resistance is 10 ohms, find the current if the resistance is 5 ohms. So it says current varies inversely as the resistance. So inversely means division. And your current is going over here. Then we have our K, and it varies inversely to the resistance. Now, what do we know? What is known here? It is known that the current is 50 amps when resistance is 10 ohms. So my current is 50. My resistance is 10. So we can just write that as a 50 over 1 and easily cross multiply. So what is my K? In this case, it's pretty simple. K is going to be what? K is going to be 100. So what does my formula now look like? Well, my formula looks like the current is going to equal 500 over the resistance. So that's what we've got. That's our new formula. Now, what do we want? We want to find the current if the resistance is 5 ohms. So that resistance is 5 ohms. So what does it look like now for our current? We plug in our current. We plug in our resistance, so that's 500 over that 5, and that reduces down, and that gives us 100 amps. So we would expect 100 amps of current if that resistance is 5 ohms. So that was question 34, and that was inverse variation. So that's inverse variation there. Let's look at another one. Let's look at 36. So 36, we're going to look at the weight of an object. The weight of an object varies inversely as the square of its distance from the center of the earth. If an object is 8,000 miles from the center of the earth and it weighs 90 pounds, find its weight when you are 1,200 miles from the center of the earth. So let's take for a moment how gravity works. Now, gravity on Earth is pretty much the same. It's always pretty much the same. But the further you are from the center of the Earth, the less you actually weigh. We don't notice it too much on an airplane because you're still way far away from the center. It doesn't change much. But what happens as you go into outer space? Well, as you go into outer space, your weight decreases, right? The further out you get from the Earth, the less you weigh, because that's how gravity works. The closer you are to the center of gravity, the more it weighs. So as you start going into the atmosphere and out into space, you start weighing less and less. So the further you are out from the center, the less you weigh. So let's set up our formula, and we're looking at inversely. And it's not just inversely, it's inversely as the what? Square. So watch out for those words like the square there. So the weight of an object varies inversely as the square of its distance. So what's our formula look like? Weight equals K over the distance squared. So there's our formula. What do we know? We have to find the K. It says our starting conditions are an object is 8,000 miles from the center of the earth and it weighs 90 pounds. So the weight is going to be 90 here. And that's K over the distance, which is 8,000 squared. Now, K can be a very, very large number or a very, very small number. That's okay. 8,000, we're going to square it. And then we're going to multiply. So let's go ahead and square that 8,000. and multiply it by the 90 to get our K. So we'll take our 8,000 and we're going to square it, and then we'll times that by our 90 here. And you can either leave it in scientific notation or you can write it in standard notation. By the way, this is in scientific notation, and you can leave it like that if you know how to work with it, or you can convert it to standard notation. How would I convert this to standard notation? Just so we remember, if I have 5.76 times 10 to the 9th, what would that look like in standard notation? We've got 5.76. We're going to have to go 1, 2, 3, 4, 5, 6, 7, 8, 9 places over. So we'll have to fill in all of our zeros here. And there should be, what? I think I may have too many. We should have a, so we'll have to move this 1, 2, 3, 4, 5, 6, 7, 8, 9 places over. Or you can leave it in scientific notation, either way. But that's our value of K. And then 1, 2, 3, 4, 5, 6, 7 zeros. And we'll put our comma there. So let me make sure it looks right. Okay, I'll write it so it looks better here. And that's your value of K. And you can keep that in scientific notation. It really doesn't matter. But we did have to square it, right? Because it says, let's read our question. What does it say? Square of its distance. Inversely means we divide. So what does our formula look like now? Well, the weight of this object is going to be K, which is this value. And if you're comfortable with scientific notation, you can keep the scientific notation. If you want to write it in standard notation, you can do that as well. Doesn't matter. I'll just use standard notation, so it's, I think, less confusing for a lot of students. Now, what do we want? Okay. Well, we need to find, or we want to find the weight. And our distance is 12,000. This is 12,000 miles from the center of the earth. So what's our value look like? Well, our weight is going to be this huge number here. And you can even just keep it in your calculator. And we're going to divide that by our 12,000 squared. And let's see what we get. Now I've got the number in the calculator right here. It's in scientific notation, and I can just keep that there. And I'm just going to divide that by my 12,000. And we've got to square it. And that gives you then 40. So that object should now weigh only 40 pounds. Now, we don't notice it much, because if we're on an airplane, that's not much of a difference from the ground level to where the airplane is. But if you start going into the atmosphere, you actually start weighing less. Gravity is less effective, less of an effect on you. And once you get into outer space, right, you're weightless because there's nothing to pull you back. There's gravity, but you're so far from the center of the earth that you don't really feel it. Because gravity is just the effects of something pulled towards something else. Okay, let's look at another one here. Let's look at question number 38. We'll do 38, and then we'll talk about joint variation. Okay, so let's look at 38 here. The illumination produced by a light source varies, and here's a key word, inversely as the square of its distance from the source. the illumination of a light source at 5 meters is 70 candelas. And that's basically the candle equivalent. What is the illumination 12 meters from the source? So the farther you are away from an object, right, what happens to the light? It's less. So that's how one makes the other one go down. Or up, or that's how they go together. They relate inversely. So one does the opposite to the other. So the further you are out, the less bright the source looks. So it's inversely as a square of the distance. So your illumination is going to be K over, in this case, let's see, inversely is the distance of the square of the distance. So that's distance squared. And our illumination is candelas, and that's basically the candle equivalent. So the illumination of a light source at 5 meters, so that's my distance there, so that's got to be squared, is going to equal 70 candelas. So let's write that as a 70 over 1. And we're going to have to square the 5 and cross multiply. And so that leaves you then with K equaling, we've got 70 times 5 squared, which is, again, your 25, right? 70 times that 5 squared is 25. And that gives you then 1750. So now, what's our formula look like? Your illumination equals 1750 divided by your distance squared. And what do we now want? We want to increase this distance to 12 meters. Okay, so we want 12 meters for the distance. Now, what should happen? If we use some common sense, what happens? The closer I am to a light source, the brighter it is, right? So if I move away, what should happen? I'm moving further away, so the light should be less. The effects of that light should be less. And how much less? By the square of that distance. So we need to find our illumination factor. And that equals your 1750. And we're going to have to plug in that 12 squared, which is 144. And let's see how many candelas that we would have. And we'll round here. It doesn't tell us how far to round. So we're just going to round, let's say, to 2 places. That should be enough. They kept it as a fraction, but I don't see any real reason to. So let's say that's going to be about 12 if we round 15 candelas. And candelas are just a way of measuring light source. Light sources. If you take a photography course and you do a lot with photography, how they measure the light in photography is by candelas. So you may see candelas there. I think these are important because if you take a physical science class or you take a physics course, you are going to do a lot of these. Setting up these ratios and proportions, solving them out, and doing the variation. Everything in the physical world is some kind of relation. Direct variation, inverse, or maybe multiple things go together. One thing always influences the outcome of another. Now, when we talk about joint variation just means we have multiple variables. So joint variation just means we have multiple variables. When we say direct, that means we multiply. When we talk about inverse, we divide. So that's going to tell us how we set these up. When you look at joint variation, you have multiple variables. Some are direct, some are inverse, but they all go together. So if it says direct, we always multiply. Inverse, we always divide. So let's look now at, how about question 46? And we talked about the car with the braking earlier, at the very beginning. This one is talking about the force you need to keep the car from skidding out on a curve. So question 46. So the force needed to keep a car from skidding on a curve varies inversely, so as the radius of the curve, and jointly as the radius, or as the weight of the car and the square of the speed. It takes 3,000 pounds of force to keep a 2,000-pound car from skidding on a curve with a radius of 500 feet. At 30 miles an hour, what force will keep the same car from skidding on a curve with a radius of 800 feet at 60 miles an hour? So there are a lot of things going on. So let's see what we have. The force needed to keep a car from skidding on a curve varies inversely as the radius. So that's inverse, that means we divide. So our force is going to equal K, which we don't know. So we'll come back to that in a minute. Inversely, as the radius, so that means inversely. So let's see, make sure it's, inversely is the radius, so there's no square, it's just radius down below. And jointly just means we have multiple variables. Jointly as the weight of the car and the square of the speed. So there's our formula, right? Radius is inverse, so it goes down below. It doesn't say direct, but sometimes it will say directly to certain pieces. Joint variation just means we have multiple variables. And now we just simply plug in our pieces. So it says it takes 3,000 pounds of force. So that's going here. 3,000 pounds of force to keep a 2,000-pound car. So that's going in for the weight. So that goes in for the weight of the car from skidding on a curve with a radius of 500 feet. So that's going down below here. And the speed is 30 miles an hour. So we're plugging in our 30. And let's work all of this out and see what we get. You can do it however you would like. I'm going to make my life a little bit easier because the 2,000 and the 500, well, those can cancel, and that's going to leave you with a 4. Right? You can do it that way. You can just use your calculator. It doesn't matter. And then we just have 4 times our 30 squared, which is at 900. So that gives you now 3,600 K equals your 3,000. We'll divide by our 3,600. And I like to make my life easier too. You can always cancel double zeros out. So these double zeros can cancel here and here. And that leaves me then with K equals 30 over that 36. And that's going to then reduce down to 5 over 6. All right. So pretty easy there. And I do a lot of things mentally like this. You could have just used a calculator completely through. Doesn't matter. I chose to just get rid of some of these things like 2,000 and 500. Those can go away. And that leaves you with the 4 there. Then I had to square it, move things around. And that gives me my K. So now we know our formula is the force required to stop a car is 5/6 times the weight of that car over the speed of the car squared divided by the radius. Right? The larger the radius, the less likely you are to skid out the curve. That's why the radius is down below. If you have a really tight curve, you're going to have to put more force to keep the car on the road, right? It's more likely to get thrown off into the ditch. If you have a really smooth, really slow curve, right, it doesn't take much force at all. That's why it's down below. The tighter the curve, the more force it takes to keep that car from going out of control. So now when we fill our numbers in, we want to find something. Okay, so let's see what we want to find. We want to find that force, and let's see what we have. It says, what force will keep the same car, so the weight and everything is going to be the same, from skidding on a curve with a radius of 800 feet at 60. So what do we know? We know the same weight and that same weight is, where did we find the weight? The weight was up here somewhere. Okay, the weight of that car was 2,000 pounds. That's the weight. Our speed we're going to be using is, we want to increase that speed to 60. And then we want to make that radius 800. So that's what we got there. And let's plug in our values and see where we're at. So what do we have for our values here? Well, we have our force, which is unknown. And that's going to now be 5/6 times the weight, which is that 2,000, times that speed, which is 60, squared. And we're going to divide that by our radius, which is 800. And let's see what that gives us here. And we've got our 60 squared. We're going to times that by our 2,000. So let's put it in the calculator so we can see what we have here. All right, we've got our 2,000. We're going to multiply that by our 60 squared, because that's our speed. That gives me that. Then we're going to multiply that by your 5, divide that by your 6, and that gives you that for the top half. And we've got 1, 2, 3, 4, 5, 6 zeros. And we're going to divide that by our 800. We'll cancel the 2 zeros out. And that gives you now, divide that by your 800. Okay, that gives you 7,500 pounds. Okay. So that takes care of that. Now I know last time we did not quite finish that 3/5. So I know we need to do a little bit over that. I wanted to make sure that we completely got through variation today. So that's why I did variation at the beginning, just to make sure we completely got through it. Now, last time we talked about 3/5, and I said I would go over with you how to do the last couple of questions. So we're going to look at a couple of those, and hopefully we can get through them. I'm actually going to work one of them out of your homework. So I'm going to do question number 9 out of your homework out of 3/5. And then you can do question 10. And again, I didn't want to do these at the beginning because I really wanted to make sure that we got completely through variation today because I didn't want to leave it half done. So we should now be able to do something like question number 9. So I'm going to work out question number 9 from your homework. This is out of 3-5. You're going to be able to do question 10. So we're going to go through all the pieces, and we're going to identify which graph it is. Now, the first thing we're going to look at is we're going to look at our verticals. And I know when we talked about our verticals, what did we do? Well, to find our verticals, we set the denominator equal to 0. And so if I do that, I've got x minus 5 equals 0. So I've got a vertical at 5. And x minus 1 equals 0. So I've got a vertical at what? 1, right? Now, what does that look like? We're going to make a quick sketch here so we can use process of elimination. So this is what we've got so far. This is going to be x equals 1. This one is x equals 5. Now, which choices can we get rid of? Can we get rid of answer choice A? Yes. Use process of elimination. I'm not going to make you graph these all the way out. What you want to do is use process of elimination. Pick points if you need to. Can we get rid of choice B? It doesn't look like it, does it? Because look here. Okay, if I draw in my dotted lines, it looks like this is at about 1, and that one's at about 5. Okay, so B could work, couldn't it? What about choice C? Well, choice C, it looks like it could work because this is at about 1. And this one over here is at 5. And D could also work, right? Because if we look at it, it looks like it's at about 1. And it's at about 5. So, by finding the verticals, we took out one of the choices. Now we find our horizontal. So let's remember how we find our horizontal. Well, to find the horizontal, what do we do? Well, in this case, we're going to need to FOIL this out. So I'm going to FOIL this out. So I've got 5x over x minus 5, x minus 1. I'm going to take this and I'm going to FOIL it. So if I FOIL, you should be comfortable with how to FOIL mentally. That's x squared here. I've got a minus 5x, minus 1x. That makes it a minus 6x here. Minus 5 and minus 1 makes it a positive 5, right? I just FOILed it out. Now, remember how we find our horizontal. What do? You divide by the largest power. And so what are we going to divide it by? We're going to have to divide it by x squared. And then we let x go to infinity. So we'll divide everything by an x squared. And I know we did this last time. And I wasn't sure if we would have enough time to get through these or not. That's why I waited until the end. Okay, now remember what happens. X squared over x squared. What does x squared over x squared reduce down into? 1. What about this? Does this reduce down to a number? No, because that's 5 over x. And as 5 over x, as x goes to infinity, this goes to what? 0. That goes to 0. And that goes to 0. So what are we left with? 0 over 1, which is then what? 0. That is my horizontal. Does that get rid of any of my choices? And it may or it may not get rid of them. I don't think it does. Okay, because we have a horizontal at 0. So this one still has a horizontal at 0. Okay, this one looks like it has a horizontal at 0. And so does this one. So those aren't done. What can we do next? Well, the next part we can do is we can see if it crosses the horizontal. We'll just have to use process of elimination. So we want to see if this crosses the horizontal. So we set our f of x equal to that horizontal, which in this case was 0. And we're going to see if it works, see if it can cross it. And if I set that equal to 0, we have 5x over x minus 5, x minus 1 equals 0 over 1. Now, in this case, it will actually cross it. Okay, because when we set this as a 0 over 1, when we cross multiply, what's going to happen here? We're in luck because that gives you 5x. 0 times that is 0. So that gives you x equals 0, which is then the point 0, 0. So it's got to cross at 0, 0. So if we go back up and look at our picture, it has to cross at 0, 0. So there better be a part of the graph at this 0, 0. Now, let's see which ones we can eliminate, if any. Can I eliminate B? Yes. Why can I eliminate B? It doesn't have the 0, 0 in it, does it? So B is going to be gone. Can I eliminate C? No, because it's got 0, 0. Can I eliminate D? No, because it's got 0, 0. Now, what's the difference? We've got it down to 2 pictures here, right? This one has here, this one's over here. What's the difference between these two? Let's look and make sure we can see the difference. Lots of differences. All we have to do is find out one of the differences. So look at this one. Okay, look at answer C. Okay, choice C, it's above here. Choice D, it's down below. So let's pick a point that is bigger than 5. Any point bigger than 5. And we're going to see what it comes out to be. So let's pick 6. And we'll see what comes out when we use the point 6. And that's going to tell us which picture we have. So we need to check a point. And I'm going to have you pick x equals 6. Any number that's bigger than that 5. So let's plug in that x equals 6 here. So let's plug that back into original function. So we need f of 6, right? And that's going to be 5 times 6 over 6 minus 5, 6 minus 1. 5 times 6 is 30. 6 minus 5 is 1. 6 minus 1 is 5. Okay, so when I plug that in, right, that gives you now 30 over 5, which is then what? 6. So I now have the point 6, 6. So when we go back up and look here, we need that point 6, 6 in our picture. And 6, 6 is about here. So it's over 6. And up 1, 2, 3, 4, 5, 6. So that means it's above the curve. So it has to look like that. Okay, it's above it. Which one does that look like? There's only one that it looks like, which is what? D doesn't look like it. Answer C. You'll do the same process for question 10. Find your vertical. You only have one, if you have any. You may not have any on 10 at all. And that's okay. You may not have any. And then you use the same process of elimination to find the correct graph. And we can go over question 10 if we need to next time. I just really wanted to make sure that I got through the variation all today. That way, if you've got questions about variation, we can go over it next time. So let me go ahead now and pass out our sign-in sheet. And what's the homework, just so we know? Well, the homework, you should be able to finish 3.5. And 3.7. You should be able to do them all. Let me find the sign-in sheet here. Left over from last class period. Yep, I've got an extra one here. That's intermediate. You should write one. No, that's, I just gave out another one. So let me get you the right one. Okay, I just had it a second ago. Make sure you sign the sign-in sheet. And if you still need to take your